I would like to invite you to consider how to perform simulation. And our first example, we want to generate random numbers between 1 and 100. And definitely we just want 10 numbers. So I'm going to sample from 1 to 100, 10 of them with replacement. And what that means is that if there is replacement, there are chances that some numbers will be sampled more than once. You can increase the numbers you want. For example, maybe I want to do 14 numbers between 1 and 100, and I am able to just sample a set of numbers. And this is very important to be able to do. Another example, we want to simulate from a die, a fair die, maybe 10,000 times or thereabout, and then we see how many times and 4 appears. So I'll set the seed. You can set the seed to any number. I'm setting the seed to 823. I'm going to simulate or sample 1000 times, and that is my n with replacement, and then I sum all the 4 that will appear. So if I was to do this, what I mean is, for example, if I look at the number of rollings that I've done, you can see that it will be between 1 and 6, and there are 4. So here the second line here is I sum all the numbers that are 4 and then divide by n, and then it will tell me that I have 0.175 chance of picking a 4. But in actual value, because there are 6 numbers, the probability of picking a 4 should be 0.166. So now what I want to do is to see if the probability that is coming up can be accuracy can be increased. What I'm going to increase is n. I'm going to increase it from 1,000 to 10,000, and let's see what happens. And what happens to my value? My value now is 0.1603, and remember the actual value is 0.166. What would happen if I was to increase this number again from 10,000 to 100,000? Does it change anything? Let's find out. You can see it becomes closer to the actual value, which is 0.166. And so the more the number of simulations you are doing, this we have said is 100,000. What about if it's a million? N is 1 million. What happens? That's what we want to find out, what could happen if you are to increase. You see what has happened. The value now is 0.166957. So the more I increase, if I put 10 million, it will take a little bit longer, the process. But for sure, we are going to most likely get a value that is almost as accurate. Now you can see it is 0.167, and so on and so forth. So that's how you increase the accuracy in simulation or in sampling here as you're doing, by increasing the number value of n. The next one is about a fair coin. We want to estimate the probability of getting ahead. We know that the actual probability is 0.5. So I'm going to sample between 0 and 1 and see what I'll get. Let's see the probability of heads. The actual one is 0.5, but you see ours is 0.4987. This is 10,000. If I increase it to 100,000, I would expect also the value. You can see it's getting closer and closer to 0.5. If I add 2 more zeros, that makes it 10 million, and I can make it 100 million. The more the samples you're going to do, the longer it will take to generate the solution. But chances increases that the value you're going to get is the accurate value. You can see now what I'm getting, 0.500269. But you see it is taken a little longer. because of the many samples that you're going to get from there. It does it 100 million times. Now, I want to briefly introduce Monte Carlo, and I want to estimate the integral of x squared from 0 to 1. If you are to do integration from 0 to 1 of x squared, that will be x cubed over 3. And if you replace the 0 and 1, you get that the answer is that. So, how do we go about it? I've set n to be 10,000. Learn if is used for uniform distribution. I want it to give me 10,000 and the value should lie between 0 and 1. Then I define my f of x to be x squared. So I say the integral estimate is the mean of f of x. Uh, Remember, I've already generated x here. So if I came here at this point and checked what are these values of x, those are all the different values of x that have been simulated between 0 and 1. And then I define my f of x as x squared. So if I get f underscore x, is all these values. So when I say find the mean of x underscore x, and that's the value we are going to get, which is approximately closer to 1 over 3. 1 over 3 is 0.333 and so forth. So if I wanted to be more accurate, for example, if I was to reduce this to 10, let's see what answer we are going to get. You can see it's 0.13 against that. You can see there's a big difference in the solution. Yeah, but if we increase this maybe to 100,000, then our solution will converge closer to the actual value. But as I've said before, you can see what is happening. If you continue, if I add an extra zero to make it 10 million, it will converge to closer value, and you can see what is happening. So whenever you're dealing with simulation, either you are sampling or you're using Monte Carlo, even when you're doing a simple integral like this, the bigger the value of n, the more simulations you are doing or the more samples you are picking, the more accurate your value becomes, but it increases the resources of the computer that you need to be able to come up with that solution. So thank you so much for watching.